Hey everybody, Mr. Mack here. I'm doing the second part of our work with radicals. I already went through a lot of the evens through 50, and I think I'm just going to do some of the odd ones here for this next set, since there's only a couple of even problems. So let's take a look at this first problem here. I've got w to the 3 halves, root 32 minus w to the 3 halves, root 50. And we see a base of w that's the same for both of these terms. We also see that the exponent is the same, the 3 halves. Just as a reminder, the 3 here means that we're raising to a power of 3. And then the 2 in the denominator tells us that this would be a square root. So this would be taking the square root of w and then cubing it, or cubing it and then taking the square root. Either way works. But we have a radical 32 and a radical 50. These are not like terms unless the radicals are also the same. So we need to see if we can figure out, in these next couple problems, how we get a common term here with the radical and the variable with the exponent before we can combine the terms. And so 32 is definitely has factors that are perfect squares. So if we break it down into our factor tree, I hope we see really quickly when we get 16, we know 16 is a perfect square. But if I wanted to go ahead and just fully complete my factor tree, we can figure out where the pairs are and just pull that out. So I got two pairs of 2, and then I have an odd 2 here. So a 2 comes out, so let's see, I got a 2 that comes out, another 2 that comes out, and then I have this w to the 3 halves here, and then this lone 2 has to stay under the radical. It did not pair up to come out. So 2 times 2 is 4, and I hope you see that in this part, the square root of 16 is 4, and then that odd 2 would have stayed in. Okay, minus. Now for 50, if we do our factor tree, we see 2 and 25, and 25 is a perfect square. So if I were to pull that out, you see our pair here, 2 is odd. So the 5 comes out. I'm going to write the w to the 3 halves, and then I have 2 is the odd 2 that stays under the radical. And 2 times 2 is 4. So 4 minus 5 is negative 1. So this would be, I could say negative 1 or just negative w to the 3 halves root 2. And that is an ellipse. That is my final solution. Okay. I'm going to try to do the same thing here. The x to the 4th and the x to 4th, that is a perfect square, right? So if I were to take the square root of x to the 4th, it would be x to the 2nd, because x to the 2nd squared equals x to the 4th. Therefore, the square root of x to the 4th equals x to the 2nd. So I got that part is going to come out. But what about the 108? So we could do a factor tree here for 108. I know it's even, so 2 comes out. That's 54. 2, 27. Okay, 27 is not even, but a 3 comes out. 3 and 9. 9 is 3 and 3. I got a pair of 3s, I got a pair of 2s, I have an odd 3. So that means a 2 comes out, a 3 comes out, an x to the 2nd comes out, and what stays under the radical is the lone 3. Plus, I'll do the same thing here, 27. Well, I hope we see 27. Here we got 27, right? It's 3, 9, and then 9 breaks to 3 and 3. So that means that a pair of 3s would come out. x to the second comes out, and this would be root 3 stays in. We have the same variable, same exponent, same radical. These add up. 2 times 3 is 6, plus 3 is 9, x squared root 3. Okay, 53 is a good one. We have a radical here in the denominator. So when we simplify expressions, we don't like having denominators that have radicals in them. So I have 2 plus 2 root 3. This is a whole term here in the denominator. How can I get rid of this radical? So if I multiply, we know that if I have root 3 and I multiply by root 3, that gives us root 9, and the square root of 9 is 3. So if I multiply root 3 top and bottom, it will get rid of the radical here, but I'll introduce it with the 2, because when I distribute it, I'll be stuck with a radical behind the 2. So that didn't work. So what we have to think of is multiplying by another binomial that will cancel out the middle term radical here, and that is the conjugate pair. So it means that I'm going to write 2 minus 2 root 3, and when I do my FOIL on this, we'll see the middle terms cancel. And we've done a couple of the examples already, but I'll just do, so the numerator right here. So root 12 times x times 2 would be 2 root 12x. And then root 12x times negative 2 root 3, that would be negative 2. And so what happens here is 12x times 3, multiplying inside these radicals, would give me 36x. Okay? I hope you see 36 is a perfect square, so we can simplify that. The denominator, I'm going to have 2 times 2 is 4. Okay, first outer, 2 times negative 2 root 3 is negative 4 root 3. Now I'm going to do inner. 2 root 3 times 2 is 4 root 3. And then 2 root 3 times negative 2 root 3 is negative 4 root 9. Look what happens to the middle terms here. They cancel. And what's the square root of 9? It's 3. So in the denominator here, I get 4 minus 4 times 3, because root 9 is 3. In the numerator here, we can simplify some stuff. So 12 I have a pair of 2's that can come out. So this would be 2 times 2 root 3x. And then the square root of 36 is 6. So this would be 2 times 6 is, I'll just write it out, 2 times 6 root x. Okay, so 4 root 3x minus 12 root x over 4, so 4 times 3 is 12. 4 minus 12 is negative 8. Okay. Now, we can simplify some things here, and I don't like a negative in the denominator, so let's say we can take out a 4 here, top and bottom. So this would be root 3x minus 3 root x over negative 2. And then if I multiply top and bottom by a -1 to get rid of this -2 here, running out of space, that will give me a negative root 3x plus 3 root x divided by 2. I can also switch the order of this numerator, but that's fine the way we got it right. Oh, try it again. Okay, that's the hardest kind of problem, I think, in this section, where we have to get rid of the radical using a conjugate pair, and then all the simplification that goes into that. Okay, root 147k to the third. So 147 So quick trip. We know this is odd, but so 2 doesn't go in, but does 3 go in? If we add all the digits, 1 plus 4 plus 7, that gives us 12, and 3 goes into 12. So that tells us that 3 does go into 147. So that's going to give me 4. It's 49. 49 is a perfect square. So that means I got a pair of 7s and an odd 3. Now k to the third, how about I rewrite it this one so maybe we can understand what's happening here. So this is 7 squared, and then I got times 3, right? 7 squared is 49, so 7 squared times 3 times k squared times k. It's another way I can write k to the third. Well, what's the square root of 7 squared? You know the square and the square root undo each other, so that comes out. Square root of k squared is k. And then the 3 and the k are odd. They don't have any pairs, so they're going to stay in the radical. And that's it. Okay. All right, so let's see. 125 ends in 5. So hope you see a 2 goes in, or a 5 goes into that. So let's take a 5 out. So 125 divided by 5. Five goes in 25 5 times. It's 25, right? 5 quarters make up $1.25. So I have a pair of 5s and an odd 5. So how about we write it like this? Check this out. We got 5 squared. I'll do it this way. 5 squared times 5. Okay, that's the 125. How about I write this n? I can write this as n to the 5th raised to the 2nd. Remember power rule, 5 times 2 is 10? I could write it like this. Why would I do that? Well, the square root of something being squared is just whatever that base is, right? They would cancel. And so now I would get the square root of 5 squared is 5. The square root of n to the 5th squared is n to the 5th. And the only thing that stays under the radical is the 5. And that's done. All right, cooking along here. What do I want to do now? How about we look at 61? Just skip ahead here because this one's a little bit different. Okay, this right here, that 4, this means the 4th root, right? So what number times itself 4 times gives us this expression under the radical? So when we do our factor tree now, let's see if we can find sets of 4. So in 162, I got a 2 and 81. 3 and 27, 3 and 9, 3 and 3. So instead of circling pairs, I'm circling 4 sets. Okay? And 16, 2 and 8, 2 and 4, 2 and 2. This whole thing is a set of 4. We'll leave this in radical form for a second here. So I've got my numerator is going to be 3 to the 4th times 2. Now x to the 6th. How about we write this as x to the 4th times x to the 2nd. Now I'll show you why that makes sense in a minute. This is 2 to the 4th, x to the 4th. Okay, so what is the 4th root of 3 to the 4th? Okay, so the 4th, what happens to the 4th and the 4 here? They cancel, right? So the 4th root of 3 to the 4th is 3. So the 3 comes out. This 2 does not. 2, there's no fourth, perfect 4th here, but the x comes out. And what's left? Okay, that 2 is left, and that x squared is left. So I'm going to write that there. Okay, now in the denominator, both these come out, right? 2 to the 4th, x to the 4th, this would just be 2x. Now, look at this. 3x over 2x, x's are going to cancel. So this would leave us with 3 times 2x squared, 3 times square root of 2x squared over 2, because the x's would cancel. And we have to, I forgot here my 4, I got to make sure I include, this is still the 4th root of this in here. Now, let's see, maybe leave myself some space. Here, let's get this. So when we simplify this, you got to make sure that this is still the 4th root. So this is a 4 still here on the index here of the radical. And then this is still a 3 right here. Okay. And let's box in that answer. Okay. Next one. Let's take a look at 68 here. Okay, so we have our exponential terms here, our exponents are fractions. So again, this means that we're raising it to the 3rd power, and the 2 in the denominator means square root. Okay, so I could rewrite this. How about I'll rewrite all these in a different way. Let's say square root of 4 raised to the 3rd. Okay, I just translated that part. Minus. Okay, this part right here, we could do the square root of 16, and then we're raising all this to the 3rd. Okay, so I just translated that as a radical. And this one right here, we're doing this 3 in the denominator. So the way we could write this is, I put the radical here, but then I put a 3, because that's a cube. Okay, so what is the square root of 4? Well, it's 2. So I could do that part first, 2, and then I'll do the radical in a bit. Square root of 16 is 4, and then I got this radical, this exponent, 3, over. And what's the cube root of 8? Well, I hope you know that one. It's 2, right? 2 times 2 times 2 is 8. All right. Now let's take care of these exponents. 2 to the 3rd is 8. Minus 4 cubed. All right, so 4 times 4 times 4. 4 times 4 is 16. Times 4, 64. Divided by 2. So 2 minus 64 is negative 56. Divided by 2. Half of 56 is 28, so it means it's negative 28. And I'm going to box that in. Okay. I think I'm going to stop right there. Oh, I do have 72, I guess. Yeah, around 70. I'll do 70. That's an even one. All right, we have a minus root c. I hope you see that this is another example of a conjugate pair. So we're going to multiply top and bottom by the conjugate pair of a minus root c, which would be a plus root c. So let's do the numerator. A times a is a squared. I'm just distributing. A times root c is a root c. Now, we know the middle term is going to cancel on this, okay? We recognize that. We don't have to do all the FOIL. I'm just going to multiply a times a is a squared. And then negative root c times positive root c is negative root c squared, which is a perfect square. So I get a squared plus a root c over a squared minus c. And that is it. I guess I'll do 72. Let's see here. Can we simplify stuff before we multiply? I would simplify before doing anything. So 250 is going to be 125. We did this one before, right? 125. Sorry, 5 and 25. And then 5 and 5. Okay, so a pair of 5s, and these are all odd. And then the x squared is a perfect square. So what are we going to get here? A 5 and an x are going to come out. And then a 2 and a 5 stay in, so 2 and a 5 is 10. Okay. Let's see here. Well, the square root of 100 is 10. I don't even need to do a factor tree there. And then b to the cube. Well, b squared, I can take out b squared. Square root of b squared is b. And then I'm left with an odd b here. So that stays in. I mean, I hope you see that. If we take b cubed, right, and then this would just be b and b squared and b and b, if I wanted to write it out like this. And I have one pair of b's, so one b comes out, and then the odd b stays in, right? And then we've got 7 root b, nothing to do there. And then this one, 125, we already know 125 is 5 times 5 times 5. So 1 5 comes out, 5 stays in, and this x stays in too. That didn't come out. Now we're multiplying these. Now before we do that, does anything here simplify? Well, I see 5's cancel. I see these b's right here, root b divided by root b. That's going to cancel. And let's rewrite what we got here. I don't see anything. A 7 and 10, the b. So this root 10 and this root 5x, something can happen here. So I've got, no, I have an x here still. So I've got x root 10 and this 7. So I'll put the 7 in front. So x root 10 times 7 is 7x root 10 all over, what do we got here? We got a 10b here, and then I got a root 5x here. Okay, now I don't like this radical in the denominator, so we're going to multiply top and bottom by 5x. Notice this is not a binomial, this is one term, so we don't do a conjugate pair here. Okay, so 7x times root 10 times 5x, we're multiplying this right here. So I'll do that. So we multiply the radicals. Root 10 times root 5x. This would be root 50x. And this is 10b. Did I run out of room? No, I'm good. Now, root 5x times root 5x is just 5x. Right? Radicals cancel. Okay, now 50 here is 2 and 25, and 25 is a perfect square. So that pair comes out and this 2 stays in. So 7, and then I have a 5 here. So I'll say 7 times 5 times x, root 2 stays in with the x. And then I still have, I'm just going to say 10b times 5x. Okay. So look at this. You see 5x here and a 5x here? They're going to cancel. And now I'm just left with 7 root 2x over 10b. And that's my final. Very good. Okay. So a few problems there. A couple mixed odd ones with a couple of the even ones. The stuff definitely more challenging, but you know, these are kind of the problems that we want to be able to do in Algebra 2, especially moving forward. All right. I'll see you guys later. Have a good one.